So we've been talking about um, general equilibria in Edgeworth boxes where there's two consumers and two goods. And we noted that an equilibrium is a point in this box where there's a budget line which determines the things that are feasibly affordable for both consumers jointly, and the allocation must lie on that line and be the mutual optimization solution to the optimization problem of both goods, looking either in the northeast direction as from the perspective of consumer I, or the southwest direction in the consumer J. So it has to have this mutual tangency between the difference curves. This seems like a tall order. Feels like it might not exist. And so it's worth noting that three things have to hold at equilibrium. One, the endowment itself, the initial endowment of the consumers, must lie on the budget line. That's because wealth stems from the initial endowment. So if I go to the market and I sell everything at a given price, it must be possible that I can buy everything back that I just sold, right? I sell some stuff, I get $10 for it. I can use that $10 to buy that stuff at the same prices, right? I mean, that's sort of, it's almost, seems like I'm saying something magical. It's really prosaic. It literally, if you buy something at a price, you can sell it at the same price or whatever. So that means you can buy back your initial endowment, which means that the initial endowment must be affordable for both consumers, which means the initial endowment must lie on that budget line. So we need to find a price vector which goes through the initial endowment. Two, consumers 1 indifference curve must be tangent to the budget, and consumer 2's indifference curve must be tangent to the budget. And that's because they're both maximizing, given their induced wealth, given what they consider affordable bundles, they are choosing maximally. And we already know from our original part of the class that the notion of optimality here is going to be this tangency between the indifference curve and the frontier of the budget. So we have these three sort of, this tripartite condition, and that seems like it's difficult, especially if the number of goods and the number of consumers got larger. If there was 10 consumers and 50 goods, we would have lots and lots of conditions that we have tangencies in all the different places. So let's look at a quick example and see if we can find an existence of a equilibria in that example. So we're going to look at this Edgeworth box economy. So there's two consumers and two goods. It looks like we're calling the consumers A and B and the goods 1 and 2. So consumer A has a Cobb-Douglas utility function with parameter A and 1 minus A on the two goods, and utility B has B and 1 minus B on the two goods. So we have two Cobb-Douglas consumers, and they have initial endowments. Consumer A has 1 unit of good 1 and 0 units of good 2, and good B and consumer B has 1 unit of good B 2 and 0 of good 1. So these are two different farmers. They farm different stuff. A farms good 1, B farms good 2, and they don't have anything of the other good. So let's just let P denote some price vector, right? P is a price vector. It's a price for good 1, and it's a price for good 2. So there's a price for each of these two goods. And at these prices, we know what the income of the consumers are, right? Well, consumer A has 1 unit of the first good and 0 units of the second good. So if he sells at a price P1, P2, he gets back 1 times P1 plus 0 times P2, which is just P1. And analogously, B gets back P2. So the wealth, the income of consumer A is P1, and the wealth of consumer B is P2. Now, I'm not going to go through the derivation because this is stuff that we've been doing for weeks and weeks and weeks. But the Walrasian demands of a consumer with price vector P and wealth W1, or income, the wealth of good 1 is IA, right, is equal to A, the income divided by the price, and for the second good, 1 minus A, the income divided by the price. Right, so this is just, that's just given by the normal Lagrangian standard method of solving a consumer's problem. So there's nothing specific about equilibrium here. This is saying we've now determined, given this price vector, what the income of each consumer is, and those consumers are going to do the standard short-looking thing. Now, this is extremely important. This is a very key idea. The fact that we're just doing a consumer optimization problem is tantamount to saying the consumers are taking these prices as given. They're acting as if they're the consumers in our week 2, which just took prices as given. And of course, that means that these consumers are their demands will be Walrasian demands, But it's interesting because the prices aren't given. The prices are determined by their demands, right? So it's this circular, it's a very circular notion of reasoning, not in a bad way. Usually circular reasoning is bad in the sense that it depends upon itself. This isn't that it depends upon itself, it's that everything is jointly determined. It's determined all at once. So it is as if they're taking these prices as given, and their behavior reinforces that conclusion. And that's a very economic way of thinking. And that's why it's called equilibrium. The forces of demand exactly equal the forces of supply. The supply is the endowment and determines their wealth, and that determines the prices at which they make demands, which determines the wealth, and blah, 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 blah. So we can reduce this a little bit because IA is equal to P1. So this just becomes the demand from consumer A just becomes A in the first good market and 1 minus A P1 over P2 in the second good market. And we can read off the same thing for consumer B. And what we know is that in order for P to be in equilibrium, we have to have two conditions, right? The first one is that X, the endowment, the allocations are while raising demands, which means they have to look of the form up above, X star A and X star B. But the other part is now going to come into effect that this has to be a feasible allocation. The allocation cannot exceed, the demands cannot exceed the amount of the endowment. Well, we know what the endowment was. It was 1 unit of each good. So that means that the amount of good 1, A, plus the amount of good 1 demanded by A, which is just little a, plus the amount of the good 1 demanded by B, which is P times P2 over P1, must equal 1, right? It must equal the endowment of good 1, which was just 1, the supply of good 1. That's A plus P2 over P1, right? That's the amount of demand for good 1, and that has to equal 1, the supply of good 1. Well, that means we can solve for P2 over P1. We solve for P2 over P1, we get 1 minus A over B. In other words, in an equilibrium, it must be that the ratio of price 2 to price 1 is equal to 1 minus A over B. So what we get is a condition on the prices. Now, you might think that we could push this further in the sense that we could actually determine what P1 and P2 are, maybe by plugging into the demands in the second good market. Unfortunately, we can't, and that follows directly from the fact that while Walrasian demand is homogeneous of degree 0. If we double both prices, we double the income of consumer 1 also, because we doubled the prices, and that's how the income is being generated. So if we multiply all the prices by some constant scale, we multiply those prices by the constant scale, we also multiply the incomes by that constant scale. Now the homogeneity of degree 0 of the Walrasian demands mean that when we multiply all the prices and incomes by some common scale, common positive scale, we don't change the Walrasian demands, which means that the Walrasian demands are still exactly the same point, which means they're still feasible, and therefore it is still an equilibrium. So if we find an equilibrium, all we know is the ratio of prices. And this makes a lot of sense. What we care about is the rate of exchange. How much can you exchange good 1 for good 2? We don't actually care about the literal price. If we multiplied all the prices by 100, everyone would become 100 times wealthier, everything would become 100 times more expensive. We would do exactly what we were doing before. We can verify that this is a solution. We got that P1 over P2, P2 over P1 is 1 minus A over B, and so we can look at what happens in the market for good 2. If we go back to the market for good 2, we see that the total amount demanded in the market for good 2 is 1 minus A P1 over P2 plus 1 minus B. We plug in what we know about P1 over P2, and we get that this is equal to 1 minus A P1 times B over 1 minus A over P1 plus the amount demanded by good consumer B, which is 1 minus B. Well, that just reduces to B plus 1 minus B, which is equal to 1. So the market clears. Market clearing means that the demand is less than the supply. So we have found an equilibrium. In fact, we found a whole family of equilibria because we can scale up this ratio of prices by any constant we want, and it will stay an equilibrium. So we showed that we had that equilibrium in that one example, and now I'm going to go massively generalize that and say if a consumer's utility are monotone, the demand functions are continuous, then a Walrasian equilibrium exists. This is an extremely general and extremely powerful result. It's not talking about Edgeworth-Box economies. It's talking about general exchange economies. We don't even need concavity here. It's enough to be strictly monotone, to have non-satiated preferences and continuous functions. And it's a very interesting proof. The proof is far beyond what we can do in this class, not necessarily because it's very difficult, although it's pretty difficult, but also because it just takes a little time to set everything up. But I'm going to leave this here, and so if anyone's actually interested, you can pause this and just take a look really quickly, get a sense for what's going on, come ask me about it, or look in the book or look online for existence proofs of general equilibria. This is enormous. This has its own literature, right? Existence in general equilibria is its own thing. People have written books on this, weakening the conditions, showing it holds for more complicated markets, all sorts of things. So there's a couple of assumptions that we used, and while we're not going to go over the proof, it is worth noting where those assumptions play a role. So one, we said that demand functions are functions, so they're single valued. In other words, I demand a particular bundle. My wall-raising demand demands a particular bundle rather than a set of bundles that are equally valuable to me. We can relax that. That's unimportant. We just use a stronger fixed point theorem. It's fine. Continuity of demand then has to be replaced by something weaker, which works for sets, right? Because continuity means that the value of the demand changes continuously. Well, what does it mean to change continuously when you're demanding a set of things? We just need to replace it with upper semi-continuity and we're fine. The utilities are monotone or strictly monotone. That again can be weakened. It can be weakened to something called local non-satiation, which we didn't really talk too much about in this class, although I've hinted at it. And just the idea that if you move in some direction, you do better. Maybe not in every direction. So something like, those minimum preferences, those perfect complements, they're not strictly monotone because if you move just straight up on one of the axes, you don't do better, right? But they are locally non-satiated because you could always move diagonally and do better. And that's actually enough for all of this. The demand functions are continuous is actually a very critical assumption. Without continuity of the demand functions, an equilibrium may not exist. And I think in class we'll go over an example of that, although right now I'm not going to bother with the video. But this is problematic in particular because continuity can fail in subtle ways, right? It can fail as the price approaches zero. And two different goods could approach zero at different rates, right? So we could take the price down to zero for two different goods at different rates. And the entire time you might want a bounded amount of one of the two goods. But when the prices actually reach zero, all of a sudden your amount is unbounded. And this can be a problem. So a lot of times the way that this is gotten around is, I have an example, but this is the example I'm not going to worry about. What you can do is you can just assume that the initial endowments are interior, and that usually kills off this problem. I'm not going to give you any kind of wacky thing where there's the existence. So you don't have to worry about this too much in terms of the class, but it is valuable information to have in your arsenal.